Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Large-Scale Mathematical Model Structure. It corresponds to one of several short conferences, in which the advances of HI research are presented, on the topic of artificial brains and decision-making artificial intelligence. The list of short introductory lectures to decision-making artificial intelligence are presented in the picture. Large-scale mathematical model structure. The solution of an optimization problem using large-scale methodologies is based on partitioning the problem into two sub-problems that must be solved in coordination. It can be said that there are two basic methodologies that bring together majority of applications: Bender's partition theory, BT, and Lagrangian relaxation, LR. They can be considered complementary. In BT, the partition is performed according to the variable's type. It is a primal method that works on primal feasible zone. In LR, the partition is performed according to the constraints type. It is a dual method that works on dual feasible zone. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Bender's partition, or Bender's decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. This block structure often occurs in all real applications. The large-scale methodologies allows to divide a monolithic problem into multiple problems that can communicate to each other. Partitioning and decomposition divides the problem into multiple subproblems, represented in the diagrams by colored submatrices, which link them to subproblems. Depending on its complexity, the ways to divide a system may be non-numerable. In the image, the green diagram corresponds to the matrix, and the blue diagram to the associated hierarchical structure. The diagram shows a two-level structure. This diagram shows a three-level structure. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. The hierarchical structures produced by large-scale methodologies do not simply correspond to mathematical artifices to solve large-scale problems. These structures are linked to representations of reality. To model a real system, two visions are possible. Top-down implies a monolithic vision, based on sequential synchronous mathematics. From the bottom up, a parallel atomized vision, based on parallel asynchronous mathematics, oriented to large-scale optimization methodologies. This hierarchical approach can be changed by the vision of an artificial hypothalamus, in which the problems work cooperatively, and have a protocol of communications between them, to solve a common problem, running in parallel. The mathematics to solve these multi-problem parallel processes are already developed and proven. In 1983, Tony Van Roy created the cross-decomposition approach, to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. Again, the difference that the domain of large-scale optimization creates with respect to sequential optimization, is a chasm, not a gap. Velasquez Bermudez has written several papers contain information related to the solution of large-scale mathematical problems, using decomposition and multi-level partitioning, Bender's partition theory, Lagrangian decomposition theory, cross-decomposition, and asynchronous parallel optimization. The documents cited can be useful for working on large-scale mathematical modeling. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied.